I want to thank the chair for allowing me to present at the NETS conference today. The topic we're going to be presenting, or I'm going to be presenting, is power in the next era of nuclear fusion and quantum computing with Lunar Helium-3. My disclaimer is I am not a physicist. My background is more in planetary geology, engineering, mining, and systems engineering. My bio is up here just for context of the presentation today. My key background with relationship to helium-3 goes back to planetary geology, where I first learned about helium-3. I then went on to get additional degrees in engineering, mining, aerospace engineering, as well as I'm in the process of finishing my PhD in engineering mining. All of this to give me a better understanding on the possibility of extraction helium-3 from the lunar surface. Now, the singular focus of our company is on the extraction of helium-3 from the surface of the moon to provide fuel for nuclear fusion reactors in the future, along with quantum computing. The source of helium-3, as a reminder, comes from the decay of tritium on Earth. There's estimated less than 10 kilos in the United States at the present moment. More organically, helium-3 comes from the sun. It travels in the solar wind along with helium-4. It gets captured in our atmosphere, making it basically impossible to obtain on the surface of Earth. However, on the moon, with no atmosphere, it's been baked into our regolith, or the regolith of the moon, for billions of years. The good news is there's an estimated 1 million tons of helium-3 on the surface of the moon, plus or minus. The bad news is its concentration is extremely low, at about 1 to 15 parts per billion. Now let's look at a hypothesis on how helium-3 is retained in the regolith. There's at least 3 ideas. Probably they all do work or exist in different combinations. The first and most prevalent is from the solar wind. It's found between the regolith grains, mainly at the surface, as it cannot penetrate deeper. Second, also initially coming from the solar wind, but has now more of an impact origin, is helium-3 that may be embedded or related to crystals from temperature and pressure from meteorite strikes. More than likely, we're going to find this at depth and concentration. Third is a chemical origin in which there may be chemical affinity for helium-3 with certain minerals like ilmenite. So we got at least 3 hypotheses on how to find helium-3 within the regolith. All 3 of these may be active, and there more than likely is other ways we're going to find helium-3. With respect to depth, many people believe, including ourselves from our company, that the bulk of the helium-3 is at the surface, as there's been a lot of baking of the regolith from solar wind for the past 4.5 billion years, whereas the impacts, the meteorite strikes, are by far less now than they were billions of years ago. So let's talk about 2 use cases for helium-3. The most important for today, because the audience is our physicist, is on nuclear fusion. We are out talking to many other societies and conferences besides fusion. We're talking to quantum computing companies and conferences. We are talking to aerospace conferences, and also those that are concerned about the ecology and the ecosystem on Earth. The way we describe fusion to them is fusion 1.0. We've coined that term when fusion is done with tritium. If you had helium-3 and could get access to it, we believe that will be an upgrade. We're calling that fusion 2.0 with helium-3. Now, the general public and many people understand somewhat about fusion, but the way we describe fusion 2.0 is that it will be the first true green energy, unlike tritium. It cannot explode, which is similar to tritium, but it has no byproduct storage, which tritium requires byproduct storage. It's more safe because the output includes a proton, not a neutron, and it has a higher energy yield. So the take-home message, we believe, is that fusion 2.0 with helium-3 is the ideal fuel source, but because it will create the opportunity for the world's first global green energy. Now, in broad stroke numbers, if the entire world went to nuclear fusion with helium-3, again, helium-3 to fuel it, which we call fusion 2.0, if this took place across the globe, if you extrapolated out the numbers, first off, roughly the average helium-3 fusion reactor may need plus or minus 200 kilos of helium-3 per year. You would need about 2,800 fusion reactors across the globe, and roughly they would consume about 570 metric tons of helium-3. Now, these are broad stroke numbers, but I think the numbers are within reason here. The second use case, which is important to be aware of, even though this is a fusion conference, is quantum computing. So while quantum computing is still experimental, it's advancing rapidly, and I love this example. If you took a classical computer and had an equation that was difficult, and it took a classical computer 10,000 years to solve, a quantum computer can do this similar equation in approximately 8 hours. It's significantly faster. The potential applications are mind-boggling, including cryptography, drug discovery, cancer treatments, and from a political point of view, whoever controls the first quantum computing may hold informational strategic dominance. Well, what does this have to do with helium-3? Well, you need helium-3 to cool down quantum computers down to near absolute 0.01 Kelvin. Without helium-3, you cannot cool them down nearly as close to 0.01 Kelvin. Errors take place, and it doesn't function nearly as well. From a numbers point of view, each quantum computer in the future is estimated to need about 1 to 10 liters of liquid helium-3 for cooling. There's no estimate of what the future may hold as far as numbers, so we took a rough estimate of the potential of 10,000 quantum computers across the globe in about 15 years from now. If you extrapolate all this out, 10,000 quantum computers would need about 4 metric tons of helium-3, by far less than a fully up and running nuclear fusion process using helium-3, but still very important. Revenue projections. Now, these prices are estimates based on today's dollars. It more than likely will fluctuate, but today's helium-3 prices are roughly $30,000 a gram, or $30 billion a metric ton. And again, these prices will go up and down based on market conditions. As we mentioned earlier, if Fusion 2.0 is adopted across the globe, you'd need about 570 metric tons, which equates to about $17 trillion in revenue. On the quantum computing side, you're looking at about $119 billion of revenue for about 4 metric tons of helium-3. Again, $17 trillion, I highly doubt it's going to hit exactly 7.1 trillion, but it might be 5 trillion, it might be 20 trillion. These numbers are still staggering. We believe, and here's a bold statement, the only business reason to go to the surface of the moon is to extract helium-3. And the way to make that profitable is when these three things come together. Without these three things, it will not be profitable. Number one is a reduction in transportation cost. We're seeing a reduction in transportation cost when we talk about going into low Earth orbit. The price to go to low Earth orbit has come down dramatically. We expect the same reduction in proportion will take place with repetitive trips to the moon. Second is commercialization of fusion. And your society and conference is here to discuss fusion. So if you adopted fusion across the globe, which is in the near future, and use helium-3, that will be the second part of the success triangle. And third, which is what we're going to spend the bulk of the remainder of our time on, is to go to the surface of the moon. To mine the moon, you're going to have to use lunar-based techniques and not Earth-based techniques. It sounds a little bit ambiguous, but if you go to the moon using Earth-based mining techniques, it will fail. Let's put some perspective. Now, this image, we generated this, but if you go to the internet, you search Lunar Helium-3 mining rovers, you're probably going to find something that looks similar to this. In concept, there's a device that grinds up the ground and drives the regolith that's ground up inside the rover for processing. In addition, there's moving parts. So in summary, what you're seeing here is a concept of what many people believe helium-3 mining will look like on the surface of the moon. There are two major things with this, and there's probably more. The energy of extraction is extensive, and the amount of moving parts are a lot. So keep that in mind over the next couple of slides. So let's talk about two specific challenges, and there's more, that impact lunar helium-3 mining. The first is its concentration, which is extremely low. The good news, as we mentioned earlier, there's about 1 million tons estimate, plus or minus. It's just in low concentration. If you compare this to, for example, an Earth copper mine, at about 0.5 parts per 100, the concentration delta is extremely different between a mining process to extract helium-3 versus copper, gold, or lithium. The energy required to extract copper, gold, and lithium is very high. The energy to extract helium-3 using the same process would just not be practical. The only solution that makes sense is what we've done. We've adopted a low energy extraction process designed for 1 part to 15 parts per billion. Second challenge to talk about is the lunar dust itself. It's not Earth-based dust. There's been no erosion from wind or water, so it's sharp or spickly, similar to what you see in that micrograph to the top right. It's about 45% high in silica, charged from solar radiation, so it could levitate. It's magnetized, so unlike Earth-based dust, it's exceptionally abrasive and clingy. We were warned about this by the Apollo astronauts from the 1960s and 1970s to solve this problem. So putting this dust issue in perspective, let's take a snapshot look back to 1972, the last time humans stood on the surface of the moon. Apollo 17 was the longest time on the surface of the moon, with 3 EVAs by the astronauts on the actual surface. During that relatively short period of time, the dust caused destruction, erosion, compromised EVA suit movement, and adhered to virtually everything. So we believe one of the solutions or minimizing the dust issue is to use minimal moving parts. If you remember that graphic I showed a couple slides ago with a lot of moving parts and a process that required a lot of energy, we've adopted the opposite approach, an approach with low energy extraction and minimal moving parts. Brief note about our company. When we formed it a couple of years ago, the whole idea was to take our team, make them think outside the box, and to work with the lunar environment and not against it. That has been very, very helpful when it comes to us adopting processes for extraction. The singular focus of our company has been to efficiently extract lunar helium-3 and economically return it to the surface of the Earth. If you look at the graphic, we target or work within 5 major steps: targeting at the surface and subsurface, heating the regolith, directing the vaporized gases, separating the gases, collecting them and condensing them down into liquid form. We've used a diverse team with expertise in a broad set of disciplines. We have 10 issued patents with more coming. We are presently trying to advance our TRL level, and we are looking for strategic partnerships now because there's no one company that can take on this challenge of extracting helium-3 by themselves. Thank you for your time allowing me to present at the NETS conference today. If you would like to, please reach out and take a look at our website at lh3m.com. We appreciate again your time today. Thank you.